Hello, everyone. So these are notes on air pollution that we're going to be looking at today. So let's just start talking, first of all, about what air pollution actually is. So if you'll recall, I gave you some notes on the water pollution about pollution in general. So pollution is anything that is going to have adverse effects. And the adverse effects are usually on the environment or on humans, things like human health and so forth. Now, we usually kind of put some parameters around here when it comes to how we can regulate these things, and I'll talk a little bit more about that as we go along. All right, let's get started. Here is a link, and I actually shared this link with you in Canvas so you can get to the reports on air quality and look those things over. It's really quite interesting, of the EPA's data that they have on air quality. So I just encourage you to go have a look at some of those sites. The national trends is also on there as well. And one of the things that you're going to see that's happening with the trends from 1980 to 2009, as this shows, is that they are going down. So this has been a very positive thing, and this is because of grassroots efforts that have been going on since the late 1960s. So I'll talk a little bit more about that as we go as well. All right, so in the past 30 years, you'll see that our outdoor quality has greatly improved in developing countries. This was because people they kind of got fed up. So essentially, if you can see the air that you're breathing, that's a bad thing. We generally don't like to see our air. And so people began to question what was going on because we could see the air in front of us. How do we fix these things? Is there a fix for these things? And so the answer was yes. And what this led to, when it says pass and enforce laws, we have a couple of them here. One is the Clean Skies Act, or the Clean Air Act, sorry, the Clean Air Act. And then the other one is called the Clean Skies Initiative. Okay, so those are the two big ones that came about in the 1970s. All right, Clean Air Act is the big one, and it basically set the limits for different air pollutants that they identified, and then this Clean Skies Act went a little bit further on those as well. Now, both of these have come under kind of lax deregulation, and the more we deregulate things, the worse our air quality is getting. So we're making steps going backwards now because of the fight against the Clean Air Act. And most of this is driven by lobbying by corporations or groups, mostly corporations. Okay. All right, so in order to understand the air pollution, we need to go back and look at a couple of these cycles. So the first one is the carbon cycle. And if you'll notice in this particular graphic, we have the carbon cycle on the land or the terrestrial part, and then our aquatic carbon cycle. So we have our carbon sinks. Let's just show those. So here on land, our carbon sink is mostly in the form of coal and gas, right? And that was because of the gas was formed from decomposition, microbial decomposition. And then most of the coal comes from dead plant matter. So it's taken in, and the dead plant matter falls down and then forms the sink. So that's kind of how that is. Now in the ocean, if you'll remember, what we have is our sinks are mostly oil and limestone. And remember, the limestone is calcium that's stored, calcium carbonate that's stored from shells, and the oil is from dead plant and animal matter falling down. All right, you'll notice that the big two things here, we have photosynthesis. Change that back. So we have photosynthesis is the one that's going to draw in the carbon. All right, so it's going to take CO2 and it's going to convert it then to the glucose. And then we have respiration, and that is basically going in the other direction. It goes from the glucose or the plant and animal matter, and then it is converted back into CO2. Now, respiration is done by plants, animals, bacteria, fungi, the whole 9 yards. That is the main one that goes on here. The other one that we have is anaerobic. Whoops. Basically fermentation. And the fermentation process is going to convert glucose or plant matter, animal matter, into methane gas. In both of these instances, we have carbon that was trapped or held in reserve being converted back into gases. Okay, so that's the big thing here. This one is a trapping of carbon. That's what photosynthesis does. This occurs both on land, our terrestrial picture, and also in the water as well. Now, you'll notice that the gas exchange in the ocean has been more in a positive direction than it has been in a negative direction. But that has altered and changed over time. The big one here is fossil fuels and what goes on. You'll notice cement. So cement essentially is making rock out of other kinds of material. And when you have to make rock, you have to use a lot of energy in order to make that happen. So cement making is actually one of the biggest uses of fossil fuels that are out there. All right, let's move on. Our oxygen cycle, and I included that, but mostly because oxygen is, of course, 21% of our atmosphere. But as a whole, the oxygen cycle is not really seen as its own separate cycle because it's part of both the hydrologic cycle and also the carbon cycle. So there's really no need to get into it very much. Okay, nitrogen cycle. So remember, in the nitrogen cycle, we are changing it dramatically through two different things. One is through fossil fuel emissions, and the other one is through agriculture. So our agriculture is a huge release of nitrogen into the atmosphere. Now, how does this happen? It happens through the denitrifying process right here. So if you'll notice, we nitrified, we went to nitrates down here and nitrification. So our nitrates, and then our denitrifying bacteria takes those nitrates and breaks it down into our gases. And then it is slowly then released back up into the atmosphere. The big one here that you'll notice in this is N2O, which is nitrous oxide. Now, nitrous oxide is a greenhouse gas, okay? And also is some other things we'll talk about later, but it is mostly a greenhouse gas. Now, when it is released, and this has increased, these levels have increased because of our use of fertilizers. So essentially what we've done is our fertilizers that contain all this nitrogen that we've used has basically fed the denitrifying bacteria so that they are releasing more and more of this nitrous oxide into the atmosphere. The other one is our fossil fuel emissions, and I'm going to make a change in this because I don't like the way this is stated. It's basically NO2 that is released through the burning of fossil fuels. So now we have increased different kinds of gases into the atmosphere. All right. Hydrologic cycle, of course, involves our condensation and precipitation and so forth, evaporation. And that has changed the composition somewhat, though not very much, of our atmospheric composition. And then finally, our sulfur cycle. So this one's big because there are two particular ways in which sulfur can get into the atmosphere. The first one is through our natural means, which is through volcanoes. And then the other one is through the burning of coal. Now, why coal has more sulfur in it, I'm not really sure, except that it's not usually removed in any sort of refining process. So when we burn coal, we release into the atmosphere our sulfur oxides, which is mostly also called SOxes, in the form of sulfur dioxide and also sulfate. Okay, and we're going to talk about why that's important here in just a minute. All right, when we look at our air quality, we have to kind of go backwards and look at what happened in basically the bad old days. So in 1952, London had the worst set of fog days ever recorded. And the reason this happened was because of a couple things. One was the burning of coal. So London in particular loved burning coal. Every home had a coal burning like chimney or whatever. And they were burning coal as individuals on a constant basis. So it was the coal burning was releasing, once again, a lot of SOxes into the atmosphere, okay? So, and this also happened because during this particular time, London experienced what was known as a temperature inversion. Now, the book does a good job of explaining temperature inversions, but I'm just going to sort of give it to you here in a nutshell. Let me see if we have any room on the paper. I'll put it down here. So what happens in a temperature inversion is that you have, ordinarily, remember, warm air rises, right? So we have warm air rising, and we have cool air sinking, right? Well, during this particular time, London sits in sort of a depression. All right, so it's not this dramatic, but it is pretty much over here. So we have the city of London sitting down in a bit of a depression. And so as the warm air was rising, it was going up against a layer of cool air. All right, so we had warm air trying to rise, but we had a cool air above it and like cloud cover, and then there was warm air above. And so what happens is that the warm air it was basically hitting against the cool air and was falling back down to the ground. That's what happens in a temperature inversion. Now, we get temperature inversions here as well, and they're very interesting because what happens is that not only does the air molecules get trapped, but also sound waves will also get trapped, and they'll kind of bounce around underneath this layer of cool air. And so that means that on occasion you can actually hear things from farther away that you ordinarily wouldn't be able to hear. So temperature inversion was a big player in this fog of 1952. Now, London had always had sort of this, as I said, this love affair with burning coal, but they also had, it was woven into the fabric of London life. So it was not unusual for them to have these kinds of fogs that would happen. So you have this warm, moist air being held in or trapped by the cool air on top of it, and it was mixing in with the burning coal and it had a lot of soot particles in it. So we have small particulates that were also in here, like soot, right? Small particles. And so what happened was it creates what they call the pea soup fog. And if you'll notice these pictures, some of these were taken in daylight. It was so heavy that they were having a performance in the Royal Albert Hall, and the fog rolled in, and the audience members could no longer see the stage. One of the big reasons why this was so problematic was that it made a lot of people very, very sick. And they experienced a lot of deaths because of this. And this fog of 1952 was sort of a wake-up call for London. And they began to remove the ability for people to burn coal in their own homes, and it sort of changed the face of London. Now, this was, like I said, it was something that had been going on for forever and ever. Claude Monet, 1903, painted this picture of London, and you can see in the background the London fog. Think about all of the great stories that came from London in this regard. Where would Sherlock Holmes stories be without the London fog? A lot of the Alfred Hitchcock movies, there's some real famous ones. There's one called Midnight Lace that was based on what happens when these pea soup fogs would roll in. And of course, the famous London fog raincoats were part of it as well. These are just some historic references for you to see how bad this was. And here's another one from Renoir. All right, and I'll come back to this here in just a few minutes. With pollution, we're going to look at two different ways in which pollutants get into the atmosphere. One is through natural means, and one is through anthropogenic means. So once again, we understand what those mean. Okay, now, there are also primary pollutants and secondary pollutants. So I'm going to distinguish these for you. Primary pollutants are the ones that are going to be considered a pollutant when they get into the atmosphere. In other words, they're going to cause adverse effects just because of the way they are themselves. So they are considered to be primary pollutants. A secondary pollutant happens when you have primary pollutants that react either with themselves, with another primary pollutant, or with the basic components of the air. So some of these will combine with things like water vapor, or oxygen, or nitrogen. Okay, so those would be your basic air components, right? And they're going to combine with these primary pollutants to form something else. Or you may have two primary pollutants forming a secondary pollutant, and I'll go through those with you as well. Okay, so when we look at our primary pollutants, these are the ones over here on the left-hand side. So we have carbon monoxide, our NOxes, our COXes, and our SOxes. We also have VOCs, and I'll explain what each one of these are. Now what happens is that they're going to form these secondary pollutants. And most of these are photochemical reactions. In other words, they require sunlight. Okay, so in order for them to form, they're going to require sunlight in order for that to happen. Okay, so this is just an overview right here of the different kinds of ways in which pollutants happen. Now, today we are primarily focused on tropospheric pollution. We are not going to deal with stratospheric stuff until we get to ozone depletion. Now, remember, we are distinguishing between the ozone depletion and air pollution. Today, we're strictly looking at air pollution. All right, we've done a lot to clean up our atmosphere, as I've mentioned before. We've made great strides in the past 40 years to clean up our atmosphere. However, it's not the case everywhere around the world. So we know that there are places across the world that are experiencing a lot more air pollution. And the reason they are is because they just don't have the laws to regulate these things, or they're very poorly enforced. Now, one of the things we've known when with the COVID situation, or the corona situation, is that because of shutting down certain things, we have seen drops in many of these air pollutants. These are probably temporary, but they are making a huge difference. So what is this? Why is this important? It's important because our air and water, air particularly and water are shared, right? In other words, we cannot say, well, this is my air, I'm going to do with it as I want, because air travels. It travels across the globe. Water as well travels. So we're sharing all of these things. And if one part of the world suffers, we all suffer. The other thing is, because the U.S. has moved from a manufacturing society to a more service-oriented society, we have sent all of our manufacturing to places like India, like China, like Bangladesh. And what that has done is it's made their air quality worse because they're making all of our own goods. So, are we responsible? I would make the argument that yes, indeed, we are responsible. Some of the things that I saw reported in this crazy time we're in is that for the first time, the Himalayas have been visible in about 30 years in parts of the world that they had not been before. So, kind of interesting. All right, we're going to look at two different kinds of smog. All right, so the first one is called brown smog. Brown smog is a photochemical smog. So what happens is you take your NOxes. So we have NOx, and most of this comes from automobile or vehicle exhaust. So automobile exhaust releases NOx. And the NOx means it's probably NO2, but it could be a different set. So this one is the primary one here. And what happens is it combines with another automobile exhaust, which is called VOCs. And we'll talk about those here in a second. And what they do is they produce ozone, O3. Now, this has to be in the presence of sunlight, so this is a photochemical reaction that takes place. So we have our sunlight, and it produces brown smog. So these two pictures that you see here, you have LA, Los Angeles, in 1968 and 2005. And you can see that the air quality has greatly improved in that time. And that has come about because of the regulation on these NOxes. So lessening automobile exhaust has definitely improved the air quality, and VOCs as well. So we can regulate those things if we know they are causing problems. When I was a kid, there was a lot of jokes, like late night comedians would make fun of LA smog. It was a big deal. It was very harmful. It rivaled what you see in some India cities and in some Chinese cities today. And it was very bad. So California kind of jumped on this early and started making improvements. Now here's another reason for why this is problematic. So what you have is you have air moving in from the ocean, right? So you have LA sitting right there. And on the other side of LA, so LA is right here on this coastline, are mountains. So the air would come in and blow in from the ocean, but it would get trapped. And so LA would get covered over with this brown smog. And there's a song about LA is one great big freeway. And that's kind of what it was. So LA had lots and lots of roads, and that was creating brown smog. Now you'll notice in the picture on 2005 that there is a little bit of smog left out here in the distance. So I'll kind of circle that for you just a little bit. So you see there's a little bit over here that, and you can see that we still have problems with it. Now, this brown smog gets worse in the summertime than it does in the wintertime. I'll explain a little bit more about that later. Now, LA is not the only city that suffers from brown smog. Places like Dallas also have, and the reason is because we have lots and lots of automobiles, lots and lots of exhaust traveling. The city of Denver also has it, but theirs is just the opposite. So their mountains are on this side, and Denver sits down on this side. So the air is blowing across, and it gets trapped by the mountains, which then causes it to form on Denver like that. All right, the other kind of smog is also called gray smog, and this is our London smog. So the one here is our SOx's. All right, so SOx's, and mostly combining and particulates, small particulate matter, and they go to form this kind of gray smog, and they combine with water vapor. Now what this does is it creates some sulfuric acid, but it also creates this gray smog forming over the city of London. And also, if you'll recall, this is mostly due to a temperature inversion. All right. So, pollutants. The most common pollutants we have are ozone. Ozone is a secondary pollutant. Particulate matter, and this comes from lots and lots of different sources. One is from burning things, and it could be soot. It also could be from just, exhaust coming out of car pipes. It could be from fires. It could be dust, pollen. So you can have dust, pollen, even sometimes droplets, and things like smoke. Okay. We have carbon monoxide, nitrous oxides, sulfur oxides, so our NOxes and our SOxes. We have lead, mercury, and VOCs. Now, on here, I want to say one thing. Carbon dioxide. Carbon dioxide is not considered to be an air pollutant. What? How could that be? Well, here's the answer. The EPA does not regulate carbon dioxide as an air pollutant. Okay? And the reason is because if we go back to our definition, it has to have an adverse effect, right? Well, now, it has to have a direct adverse effect on human health. All right, now we put all kinds of qualifiers in here that now remove carbon dioxide from being regulated as an air pollutant. Remember, I told you we have to tease all these things apart. So when we look strictly at what an air pollutant is, it does not have a direct adverse human health effect. Now, what does it do? Well, it causes climate change. Now, some of these others cause climate change as well. Ozone does. It's a greenhouse gas. Our nitrous oxides can be a greenhouse gas. But because they also have a direct human effect, they are considered to be air pollutants. Okay? I hope this clears it up somewhat for you so far. Let's move on. Let's look first at what our nitrous oxides are. I also shorten these down to be NOxes. So we have NOxes here, NOx. Now, these are highly reactive. They can form other compounds. And so what you see is this is our primary pollutant here, right? But then it's going to turn around and form secondary pollutants, which include things like nitric acid and nitrous acid. So our nitrous acid and our nitric acid are secondary pollutants. Okay, where are the NOxes coming from? Mostly they are coming from cars, trucks, buses, and off-road vehicles. These are the biggest sources of our pollutants. Okay, and remember, because they're coming from so many different places, this makes it a non-point source pollutant. Okay, and this is kind of important when we talk about things like electric vehicles. Now, an electric vehicle is going to, if it comes, the electricity comes from an electric power plant that uses coal, then it's still going to produce greenhouse gases. However, it's going to release carbon dioxide into the atmosphere. However, what it is not going to release, those electric cars, is it's going to cut out all of these emissions. So our NO2 is suddenly going to drop dramatically because of this. So we're now removing it from being a non-point source pollutant to now being a point source pollutant. All right. Why are NOxes considered to be a pollutant altogether? That is because they have adverse effects on the respiratory system. Most of our air pollutants do have causes to the respiratory system. So what are they doing? They're doing things like aggravating asthma, causing bronchitis. They can also cause all kinds of irritants in the respiratory system. Our next one is SOxes, S-O-X, SOx. Okay, now these also, this is a primary pollutant. Our SO2 is a primary pollutant. But they can also form to make secondary pollutants. And so our secondary pollutants are going to be things like sulfuric acid. Okay, so this one is going to lead to things like acid rain. And also you'll remember those nitric acids. Those can also cause acid precipitation as well. Okay. So where are our SOxes coming from? The biggest thing they're coming from is coal burning power plants. So mostly from the burning of coal. You'll notice that it also can come from whenever we do things like extract coal or extract metals from the ground. So some fuels will contain a lot of sulfur, but the ones that we drive, mostly like our cars and trucks, they do not release sulfur oxides. So cars are a no. They do not release SOxes. Okay, why is this problematic? Once again, it causes respiratory problems. So we're back to things like irritation of the nasal passages, bronchitis, asthma, those kinds of things. So a direct adverse effect to the respiratory system. All right, particulates. So there are two categories of particulates. We have coarse particulates. All right, these are larger particulates. So if you'll notice up here, the big concern is whether we have those coarse ones versus our fine particulates. So if they are smaller than 10 micrometers, they are considered to be a SPM, or a small particulate matter. These have big health effects, serious ones. They can cause cardiovascular problems, lung problems. They can lead to things like cancer. They've also been linked to things like obesity even, or diabetes. Now, and if you think about it, it's because they're going to work their way down into the lungs. And once they get into the lungs, they're going to start to build up. So if you think back to things like, I don't know, black lung disease and so forth, most of that came from the inhaling of these small particulate matter. This one is pretty controversial. So, in the last couple of years, the Trump administration has tried to take small particulates off the list of pollutants, saying that they could not draw conclusive evidence that there were problems with small particulates. But around the world, this is just seen as absolutely not the case. So you'll notice that most of the coarse particles are things like dust off roadways. But when it comes down to the small particulates, forest fires, power plants, and in industry and automobiles. So think about the guy, the big old Flower Mound dude riding around in his big pickup with his exhaust, double exhaust coming out the back. He is spewing small particulates. Now, would that pickup pass inspection? The answer is no. However, there are ways to get around that, and they're doing it all the time. All right, carbon monoxide. That's the one we're talking about, CO. So carbon monoxide comes about because of the incomplete combustion process. So if you'll recall, in order for something to be combusted, we have to take like our organic compound, right? Organic compound. And when it goes down, when it undergoes combustion, what it does is it breaks that compound into our CO2 plus our H2O. But in order for that to happen, oxygen has to be present, right? Well, in incomplete combustion, you are lacking oxygen. And when that happens, what it does is it creates carbon monoxide instead of carbon dioxide. So this can happen naturally, and it also can happen just in general, right, from anthropogenic sources. So one of the big sources is automobiles, right? Automobiles. They're releasing carbon monoxide into the atmosphere on a regular basis. Now, it comes out the tailpipe, and it just basically disperses in the air. The big problem with carbon monoxide is when you enclose it. So if you enclose carbon monoxide into a small space, it's going to cause direct harmful effects. And what does it do? It basically causes death, right? So how does this happen? What happens is that the blood, all right, blood holds hemoglobin, right? And hemoglobin binds with oxygen and carries it to the rest of the body. So the hemoglobin acts as like a little Uber carrying oxygen all around, dropping it off to all the cells that need it. But hemoglobin also binds with carbon monoxide. And so when it does, it's no longer binding with oxygen, it's binding with carbon dioxide. Well, the body organs cannot use carbon monoxide, and so that leads to death. And it's pretty quick. It also is pretty painless, as I've been told. I don't know if any death is painless, but there you have it. All right, carbon dioxide, once again, not an official air pollutant. All right, is it released in the burning of fossil fuels? Yes. However, it contributes to climate change, which is not that direct effect. In other words, can we link CO2 to human health problems? Yes, and we will. However, in this discussion, it is not considered to be an air pollutant. All right, our next one is lead. Now, lead was put into several products that have got it into the atmosphere. And one of the biggest ones was that it was added to gasoline. So lead was added to gasoline. Now, why did they do this? The reason they did this was they were trying to increase efficiency. In other words, getting more miles to the gallon than ever before. Now, ironically, one of the tie-ins with ozone depletion is that the same guy who invented CFCs also came up with the brilliant idea of putting lead in gasoline. Now, it did make things run better, but it also released lead into the atmosphere. So in the 1980s, the EPA decided that they needed to start regulating and removing lead from the gasoline. And this took some time for it to happen. So you'll see that it has dramatically decreased by a lot, and that was simply because we removed it from gasoline. They also used to put lead in paint, so that only when it got burned. All right, so if you incinerate it, you might release it that way. All right, and that would release it. Okay, so where today do we have problems? We still have some problems in places like lead smelters. And then they also still put it in aviation gasoline. All right, the next one is mercury. Mercury is found in oil and coal, and so when it's combusted, it is released. Now, I want to say something right here. So we usually think about combustion of fossil fuels releasing CO2, right? That's the main thing we're thinking about. But remember, coal, oil, and gas, but coal and oil in particular, are from living material, right? So at some time, they had DNA, they had RNA, they had lipids in their fatty tissues and then in their cells, the cell membranes. There were phosphates in there. Everything that was found in a living being is also found in some measure in coal and oil. So when we burn, what are we releasing? We're releasing not only CO2, but we're also releasing things like sulfur and nitrogen and phosphorus. It's PO3, I believe, and mercury, and all of the other things that were found within that living tissue. Now, what's the problem with mercury? Mercury is a problem because it bioaccumulates. And when it does, it can work its way into the food chain, which means that we are then susceptible to it. Some of the problems with both lead and mercury is that they are neurotoxins. Okay? And the other thing is that children are highly susceptible to both. So there are problems with children and fetuses. So anything that is developing is going to suffer more from being exposed to lead and mercury. Okay, our next one is called volatile organic compounds, or VOCs. Now, VOCs are what's known as, they're hydrocarbons. So remember, hydrocarbons are also found in gasoline particularly. So gasoline has a lot of hydrocarbons. And those get burned. When they get burned off, they get released. Now, how do you know if it has a VOC in it? Well, you'll notice that these are aromatics. They smell pungent. All right, so they have a very strong odor to them. So I wish I were here to ask you, so I could ask you how many of you like the smell of gasoline, because there's a lot of you out there who do. Some of you have an affinity toward VOCs. Paint. So if you've ever been in you ever painted a bedroom, what will happen many times is those VOCs will get released in an enclosed space. And what can they do? Well, they can cause things like headaches. They can cause nausea. I didn't spell that right. I'm going to try again. Whoops. Y'all don't laugh at me. Nausea. They can cause your eyes to burn. So they're an eye irritation. They can cause throat irritation. So they can cause all kinds of adverse effects to people. Now, some people don't really have much of a problem with this, but others do. Now, one of the things, though, that they've discovered is that people who've been in places like dry cleaning or other places where they're exposed to a lot of VOCs over a period of time, those people are developing problems that causes like things like hardening of the lungs or other problems associated with this. One of the big things with VOCs is this right here. So they play a big part in the formation of ozone. So ozone is, and I'll talk about that here in a second. Now, not all VOCs come from unnatural sources or from anthropogenic sources. Some of them are naturally emitted. So you have things like pine oil, which are terpenes. You have things like lemon oil or orange oil. Those are also naturally released. The Great Smokies are called that because they do release VOCs into the atmosphere, and combined with sunlight cause that kind of smoggy or smoky look that the Great Smokies are known for. Ozone. So ozone essentially is 3 atoms of oxygen. Now, these 3 atoms of oxygen exist naturally in the ozone layer, and that is stratospheric. This ozone we're talking about is tropospheric. All right, so this is tropospheric ozone. It is a secondary pollutant, right? So right here, this tells you that it is a secondary pollutant. All right, it requires sunlight. So where does it come from? It comes once again from the formation of our NOxes and our VOCs, which both come from automobile exhaust. So we have gasoline vapors are given off because not all the gasoline is burned. Some of it is just released through the tailpipe. And when those come together in the formation of sunlight, they're going to make ozone. So ozone here in the state of Texas and other places is basically known as a summertime pollutant. And the reason is because we have the sun hitting more direct sunlight. And the other thing is that we have higher temperatures, so it also uses heat as well. So what happens is that ozone isn't very stable. All right, so not stable, which means that in the morning, so in your AM, you're going to have low levels of ozone. It's mostly just going to be oxygen that's present. But as the day goes on, those numbers are going to go up. And there's several reasons for that, mostly because of sunlight, right? People are driving around more, there's more of these chemicals out there, and sunlight has to be present. Well, as the night goes on, so as it gets toward, late night, those numbers are going to start decreasing again. So it's sort of cyclical. And the reason is that ozone is not stable. In other words, it's not going to hang together for very long. So it is a summertime air pollutant. Okay. Our last thing that I want to talk about is acid rain. So, acid rain is not as big a problem as it used to be, and the reason is that because in the 1970s they started to look at how do we release or how do we reduce sulfur dioxides, and once they did, the amount of acid rain decreased tremendously. And acid rain, once again, is the formation of our SOx's with water vapor and also our NOx's with water vapor. But SOx's is the biggest one. And what it does essentially is it makes sulfuric acid. All right, now why is this a problem? Well, obviously it's harmful to plants and animals, but the other thing is that it can actually destroy things like marble. So marble gets worn down by acid rain. So if you'll notice this little statuary here, you can see very clearly that it has worn over time. And in Great Britain, because of their use of coal, they lost a lot of infrastructure. So in this last picture down here, you'll notice that the statuary from the left to the right, not only has the statuary face worn off, but if you'll look at the brick behind it, you'll see that the mortar and the brick are actually being crumbled or destroyed. And so one of the things that they really worked on was they started to see that not only did it have adverse human effects and made people sick and die, but it also had effects on the buildings that they were building. And then the other picture over here is what happens to trees. And this is an area probably where there was a volcanic eruption. And if you'll remember, volcanic eruptions release SOx's into the atmosphere. All right. And so then they combine with water vapor, and there you go. Now, volcanoes are natural. Let's talk about this one right here, this SOx. My friend Kevin, who I know on Facebook, he and I got into a big argument one day about it and about climate change. And he was arguing that volcanoes release way more greenhouse gases than humans do. And I had to just go, Kevin, I think you're wrong about that. And the reason is that SOx's, or SO2, is not a greenhouse gas. Isn't. In fact, it's just the opposite. If you get enough SO2 into the atmosphere, it's actually going to reflect more sunlight back into the atmosphere than it is going to absorb, which means that the air underneath it cools down. So one of the things we know is that if a volcano erupts, like a big one like Yellowstone were to blow, it actually is going to make everything cool. So will we have to worry about climate change anymore? That's too big a problem to worry about. Let's just don't. Okay, everything you need to know about air pollution? Well, pretty close. Thanks.